Okay, so we've looked at kind of the EM algorithm. We discussed the intuition behind it, and we um, kind of formally defined what it is and looked at an example. But doesn't give you exactly that well. That overview may not have left you with much intuition for why it works. I think the algorithm is quite intuitive. So if you're happy with the algorithm, maybe it's enough. But I think that if you're going to go further with this kind of thing, there are a couple of views of the EM algorithm that can be kind of helpful to get your intuition. And these are they're connected views, but they're down here, the variational view and the majorization, minimization, or minorization, maximization view, the MM algorithm view. So I want to just give you a quick overview of both these views. Okay, so why does it work? So let's look at the variational view first. So this is based on a paper by Neal and Hinton, so you should see that for details. Unfortunately, they use Z in their paper for the observed data, not the latent variables, so just don't let that trip you up. But the basic idea is that instead of thinking about the EM algorithm as just optimizing over parameters theta, you instead think of it as optimizing a function that depends, this function here, f, that depends not only on the parameters theta, but it's also a distribution on that depend, sorry, it's a function that depends on a distribution q, which is a distribution over the latent variable z. So for any mixture parameter theta and any distribution on the latent variables q, you define this f here to be the expected complete data log likelihood under q. So of course the complete data log likelihood here depends on z and theta, and then you take the expectation over q on z, so that integrates out the z, but it depends on q, and then you add the entropy for q, measure of the kind of how spread out q is. That's this function. So it turns out the key lemma here, which is proved in Neal and Hinton, is that when you define f this way, the optimal q for any given theta is exactly the conditional distribution of the latent variables given d and theta, which we compute in the E step of the EM algorithm. So once you've got that lemma in hand, and when you plug that optimal value in, you'll see that f up to a constant looks like the q function from the capital Q function now from the EM algorithm. So if you plug that optimal q in, you'll see, for any given q, f looks like the second term is a constant in theta. So if you just think about f as a function of theta, as a function of theta, it behaves like the q function, the EM, especially at that optimal q. So now you can think of the EM algorithm as actually optimizing f instead of optimizing the log likelihood. I mean, it's doing both. But so thinking of it that way, that first step of the EM algorithm is really finding the optimal q with respect to the function f. And then that second step of the EM algorithm, the M step, is then finding the optimal theta. And so you can think of the EM algorithm as alternating between optimizing f and optimizing, alternating between optimizing f over theta and optimizing f over q. And Neal and Hinton show that with this view, how this view leads to a demonstration that every iteration will also increase the log likelihood. So one of the reasons they are emphasizing this view is it actually allows generalizations of the EM algorithm, where you instead of optimizing f fully over q and theta each step, you just you replace these argmax steps with partial updates that just increase f. slightly. So they actually use this view to motivate generalizations of the EM algorithm as well. So it's a pretty useful view from that point of view. Maybe it still doesn't give you that much insight into why the EM is, every iteration of the EM is actually increasing the log likelihood. So for that, maybe it's easier to look at the majorization minimization view. So I guess the math is here. I'll let you go over that in your own time. I don't want to go over that, but let me just draw you a picture because I think it's going to help. So the basic idea is that if you want to optimize some function, this is our log likelihood. Imagine this represents our log likelihood. So if you can find a function, let's suppose our current value of theta is represented here, theta 0. If you can find a function that is guaranteed to be less than the function you're trying to optimize and touches it at theta 0. Okay, so it touches it at theta 0, but it's always guaranteed to be less than. If you can then optimize that function at theta 0, you know, oh, sorry, didn't mean to do that. Let's see if I can get it back. Yeah, okay. So if you, the optimum of this, sorry, this minorizing function is guaranteed to be the value of F, sorry, the value, let's call this M, and let's call this F. Value of F, so we'll define, so M is going to depend on theta 0 because you're designing M to touch F at theta 0. Okay, you're designing M to touch F at theta 0 and always be less than F. So maybe I can write that down. M theta 0, theta is always less than or equal to F of theta for all theta, and M of theta 0 at theta 0 is equal to F of theta 0. Then we're going to maximize M theta 0 over theta. Then F of, let's call that theta hat for now. So that's here, theta hat. Okay. Then you know that F of theta hat has to be greater than or equal to M of theta 0 theta hat by equation 1. Which in turn has to be greater than or equal to M of theta 0 theta 0 because of the maximization. Otherwise it wouldn't be the max. Theta hat wouldn't be the max otherwise, which of course is equal to F of theta 0 by, yeah. Right. So the idea is that by maximizing this minorizing function, you're guaranteed at least to increase F. And then you could, the idea then is you can iterate that. So we haven't got to the optimum of F, but so once we got theta hat, you can now produce a new minorizing function M theta, well, it's theta hat now, but let's call it theta 1. Maybe we should have called it theta 1 all the way, right? And optimize M theta 1 to get theta 2, and then create a new M theta 2 and optimize that to get theta 3. And you can see that every step is guaranteed to optimize F. So this kind of strategy is called minorization maximization. This here. Okay, so you can, so it's a general idea, this MM, minorization maximization, or if you're minimizing, majorization minimization, it's the same idea. You can just invert everything. This is a general way of thinking about optimization algorithms, and it turns out that EM algorithm can be thought of that way because essentially the Q function is minorizing the log likelihood, right? So actually, it's not quite the log likelihood; it's this M here that I defined M. So you can think of the Q function. It's up to M is equal to the log likelihood up to a constant. So it's a technical, obviously optimizing something up to that's equivalent up to a constant is the same. I guess the constant depends on theta 0, which complicates things a little bit notationally, but conceptually, think of M as the log likelihood. So Q is kind of minorizing the log likelihood. So when we're optimizing Q, that's why we're always guaranteed to go up in the log likelihood. Okay, so I hope that gave some kind of intuition for why it works. I think the most important thing now is to go and do some examples, which will be included on the homework, and get some experience with doing it in practice.